Hello, everyone, and welcome to our live session for today, June 5th. We are excited to be here with you today. And my name is Matthew. I run the behind the scenes stuff, and I am one of the course staff for all of our online courses. If you've joined us from our classes, welcome. We are excited to meet with you in person. If you're finding us through some other means, welcome as well. And if you are interested in taking our free online astronomy classes, I just posted a link in the chat, so please go check that out. I'm just going to give a quick overview of how this works, and then I will hand the session over to Chris to welcome you, and then we'll get started. So please post your questions in the chat. I will grab them from there. Please ask your questions only once. We do see everything that comes by. We just often have a lot of questions, and I try to give a variety of people a chance to have their question answered and to cover a variety of questions. We also try and cover a variety of topics. So if it's a topic that we get a lot of questions about and we've answered in previous sessions, it may not be on the top of the list. So maybe go back and check out one of our previous live sessions and see if we've covered that topic before. And make sure that you hit the bell icon and like this video so that it gets out. If you subscribe to our channel, you'll hear about more upcoming live sessions, and you'll be notified about those. If you want to join our listserv, I posted a link in the chat, so you can join our Google email list, and we'll let you know about upcoming live sessions. I think that's it for the business. Welcome. And Chris, I will hand this over to you to get us started with today's discussion and topic.
Okay, thank you. And we started a little late, so we're going to jump right in. The floor is open for your questions.
Excellent. The very first question that we have for today is from one of our live participants who is visiting us from Iraq, who says, Dear Professor, do you believe that Planck's constant represents a fundamental barrier to human knowledge in quantum physics?
So Planck's constant is one of the very few fundamental constants of nature or physics, which is to say it's built into the way the universe works, and it essentially is a number that defines the scale at which microscopic quantum effects dominate. So it is definitely a foundational piece of physics and astrophysics. And remind me the flavor of the question again.
Absolutely. The question is, do you think that it represents, the Planck's constant represents a barrier to human knowledge?
So it is also, we just had that USB problem again. I don't know what that means.
That's right. You're still registering. It's okay.
Okay. So yes, the Planck constant is a barrier to human knowledge because it defines the uncertainty principle in terms of Heisenberg's formulation. And so it represents a floor on the knowledge we can have of the physical world, defined at a very small scale, where we can only measure combinations of physical quantities such as position and momentum or energy and time in the product of those two things in an amount that amounts to the Planck constant. So yes, it is a fundamental physics limit, and there seems to be no way around it. It's built into nature.
Excellent, thank you. I seem to be getting a little bit of reverberation. I don't know if you can turn the microphone, or sorry, turn the speaker down at all, but
okay.
There's a little bit of...
Cable is open. Okay, it's down a bit more.
Okay, sorry about that. The next question is from Jaidul, or Ben, as he's on here. Oh, actually, sorry, I have to get the question from the email. So D, we'll jump to your question. Is there a black hole at the center of every galaxy? And if so, how do we know?
We can't say that absolutely because we haven't inspected every galaxy. Some galaxies are either too far away for us to detect a black hole, or our sensitivity limit is just not sufficient to put an interesting bound on the black hole. But every galaxy we've inspected has a black hole in the sense that we know already from the hundreds of black holes detected in galaxies that the mass of the black hole scales with the old stellar population. So giant ellipticals have the most massive black holes and dwarf galaxies the least massive. And within that framework, yes, every galaxy we've inspected has a black hole. So we think it's a universal attribute of galaxies. Now we don't completely understand how that comes about. Probably there's a seed black hole that formed soon after the galaxy formed, or even perhaps before the galaxy formed, where the galaxy coalesces around it. But yes, and the way we know is we do sensitive observations of the nuclei of galaxies. Now these are dense regions of stars, but embedded in the middle of the dense star cluster is a black hole. And we find it by its influence on the stars around it. So basically the stars around it are induced into very high speeds. Instead of tens or 100,000 kilometers per second, or miles per hour if you like, the speeds are millions of miles an hour. And that indicates a super massive object that's very compact driving the stellar motions. And that's really how we know about black holes in galaxies.
Excellent, thank you very much. The next question is from one of our live participants. Ayush would like to know, given such a high position you hold in the field of physics and science, my question is, do you remain curious every day with the same energy and passion, or does it get old?
That's a good question. I'm close to 70, so I've been doing this for quite a while. You know, the bureaucracy of being an academic and working at a university is not always wonderful, and I don't always relish that every day. But even that is not, you know, odorous or malodorous compared to some things you could be doing with your life. But astronomy, no, that's always fascinating, always exciting. I'm lucky because I work in a field where discoveries are made every day, every week. So I can't wait to check in on the archive where the preprints are served, or just the news stories about what's being discovered. So yeah, it's still fresh for me, astronomy.
The next question is from Lawrence K. Hi, Professor. Have the recent reports from DESI excuse me, regarding the expansion rate been confirmed or accepted? Is the JWST useful for this kind of inquiry, or is the Rubin Observatory?
The DESI results are preliminary, so they are subject to change. But as far as the best measurement we can do with ground-based techniques on the expansion rate, and it's changed, DESI is going to be the gold standard. James Webb is not making that measurement particularly. Its prime science is not involved in the cosmic expansion rate. James Webb is obviously doing a lot of exoplanet work. It's looking at very distant and faint galaxies for the earliest versions in the universe. The Rubin Observatory, by surveying the entire southern sky, or sky visible to it, every 3 days to Hubble Space Telescope depths, essentially, and looking for variations, is going to be foundational in taking cosmology to the next level. So we should wait. We'll have to wait a few years. The first look data from the Rubin Observatory is going to be announced, and press conferences for it very soon. But we're going to have to wait a couple of years before the results from the Rubin Observatory essentially set a new benchmark in our precision measurement of the universe.
Excellent, thank you. The next question is from one of our live participants. We see molecular clouds producing organic materials without any human intervention. Could these clouds be likened to self-powered cosmic reactors? And what unique conditions allow for this complex chemistry?
So molecular clouds are fascinating places to study in the universe. They're difficult to study because they're fairly dense. They're full of not just gas but dust, and dust obscures optical light. So essentially, most molecular clouds are impenetrable to optical observation, and we need infrared or radio methods to see inside them. And with those methods, we can see all the way to the center of a molecular cloud. The giant molecular cloud in Orion is a good local example that we've studied in detail. The conditions that allow for organic molecules to form are the fact that the centers of these clouds are quite cold, temperatures of 20, 30, 50 Kelvin. And that allows even fragile molecules to stay together, because molecules will dissociate or break apart into their constituent atoms if the temperatures are very high. So in these shielded, dark, dusty regions that are cold, molecules can form. And in fact, molecules can form more easily on the surface of dust grains. Dust in this context doesn't refer to the kind of dust you might have in your house. Dust grains are tiny microscopic particles of either pure carbon or graphite or silicates, silicon dioxide typically. So tiny grains that are micron sized. And molecules can form on these grains and then they can become more complex. So these surfaces are places where complexity can build, only up to a certain point. Although there are over 200 different molecules that have been observed in the universe, in the interstellar medium, and in molecular clouds, most of them only have 6, 7, 8 atoms. I think the biggest maybe have 15 or 16 atoms. But they're very interesting organic molecules, and indeed, some of them are the seeds, we think, of biology.
Excellent, thank you. The next question is from John McKinney, who's on with us live, and asks, is there a theory or scenario afloat that would envision our ability to someday measure dark energy directly rather than by inference via telescopes and mathematics?
It would be nice, but I don't think that's in sight, actually. I don't think that we have a prospect of measuring dark energy directly. Dark energy was discovered, of course, by its influence in the cosmic expansion rate. So 20 years ago, essentially, 30 years ago, 1995, two groups measured the accelerating expansion of the universe, which they inferred was caused by an entity they called dark energy. We don't really know what it is. It's just some agent causing space-time to expand at an accelerating rate. And in the time since then, the 30 years since then, we found various indirect ways to measure dark energy in terms of its influence, for example, on the way clusters form in the early universe, in the way light travels in the universe bent by gravitational lensing, but also influenced by the dark energy in the voids of space. These are still indirect methods. To make a direct determination of dark energy, we'd have to know more about it. We'd have to know what it is. And since it's a property of the vacuum is, of course, almost by definition, a very hard thing to study directly. So we don't have any direct methods at the moment, and I haven't heard of any on the horizon.
The next question is from Tanya, who asks, which are some good research areas in astronomy and astrobiology? And I'm assuming that, they're from a student perspective, maybe getting into the field. Where do you see as good opportunities for people in the future?
So in general astronomy terms, cosmology is very active, very hot. You can make a measurement of that by saying that roughly 40% of the time on the Hubble Space Telescope or the big ground-based observatories and their biggest telescopes goes to study cosmology. And if you throw galaxies in, maybe that's closer to a half. So galaxies and cosmology are still very active fields, and there are big unanswered questions. The nature of dark energy and dark matter, when the first galaxies formed, when the first black holes formed, and which of those two formed first. So I would say those remain very active fields. There are fields of stellar astrophysics that are very interesting too. For example, the mechanisms and study of supernovae, and particularly also stellar remnants like black holes and neutron stars. In astrobiology has become a very hot field. In some perspective, students in astrobiology worry that it's getting overcrowded or maybe saturated. And that is true, but only if there's no new data. So the new data keeps coming along, and that fuels more research projects and attracts more interest. And the big questions there are the ones they've been for a few years, which is what's the full census of exoplanets? What's the full underlying population, independent of filters imposed by observational selection? What is the nature of habitable planets? What does it take to make a habitable planet? How close to an Earth-like object can we find, an Earth clone, for example? And of course, the fundamental question behind all this is there life on any of these planets? And there are several research approaches to that.
The next question is from Jahidul, or Ben, as he's also on with us live. What is the conformal cyclic cosmology hypothesis proposed by Sir Roger Penrose? Can you kind of explain how that works?
So Penrose, several decades ago, this is not a very new theory, was worried, as other cosmologists were, about the singularity, the nature of the Big Bang as a singularity. And so he, Stephen Hawking, and other cosmologists have formulated cosmologies that are cyclic, or essentially avoid the singularity, or the fact that the singularity is the beginning of everything and you cannot interrogate the universe before the Big Bang or before the singularity. So this conformal cyclic cosmology is a clever way to make a theory that's consistent more or less with all the data we have, but posits that our expanding universe was not the initial event, and that there were previous events, and this process has perhaps been continuing forever. So you no longer have an origin 13.8 billion years ago and that's it. You have a possibly infinite progression of universes expanding and contracting, or bubbles forming in an underlying higher dimensional medium. Proving the cyclic cosmology is quite challenging, and it hasn't made enough unique predictions that it's either been confirmed or disproven.
The next question is from one of our live participants. Stardust would like to know your opinion on how does one become an astronomer, or precisely what qualifies someone to be called an astronomer. Is there some kind of certification? Are there other factors? And I'll just mention, historically, there were people who worked at observatories who became astronomers who had no formal education. Is that still possible?
Yeah, it's getting less common in modern science. Of course, training and coursework and degrees are sort of the measurement of success and progress in a field. So it's much harder. I mean, there are amateur astronomers, of course, and we've had questions and discussions about that on this show. But generally, the foundation of astronomy is physics, and so most professional astronomers did a first degree in physics, or physics and math, or perhaps physics and astronomy. That's the base coat of paint for astronomy. And then you move on to graduate school. You can do research, of course, as an undergraduate. You don't need a PhD to do research. And to be honest, you don't actually need a full degree to do research at all. Historically, of course, that was always the case, because many astronomers who did quite interesting and exciting things and made major discoveries did not have formal training. They were self-taught. So you can be a self-taught astronomer and learn the field and learn the mathematics and the physics you need. But if you want to get a job in astronomy and be paid to do it, then you need a situation where your qualifications are verified. And the typical way that happens is by having degrees. And so that's sort of how the field ends up settling on degrees as a qualification to be called a professional astronomer.
All right, one more kind of career-related question. Tanya would like to know, can an evolutionary biologist contribute, or how could an evolutionary biologist contribute to the field of astronomy or astrobiology?
Well, evolutionary biology is a very important field relative to astrobiology. So even though astrobiology is in its early stages, we have the prospect of a lot of life in the universe, many habitable worlds, many of which are Earth-like. We have no detection of life anywhere else of any kind, even microbial life. But in the prospect that it does exist out there, and it's just a matter of time before we find it, then evolutionary biologists can weigh in on how life progressed on Earth. And so what are the prospects, given the starting point of a habitable planet with microbial life in a primitive form? What are the pathways by which that life might evolve? And if the conditions, the physical conditions on that planet, its atmosphere, the sort of salinity and pH of the oceans and the nature of the geochemistry of the rocks, if that was different, then that would affect how the organisms evolve. So evolutionary biology definitely has a role to play in astrobiology as it emerges from its infancy and becomes a subject of serious study.
The next question is from an email. Wendy asks, based on the early highly evolved galaxies discovered by the Webb telescope, is it possible that the heavy elements are forged from sources outside stellar interiors?
It's an interesting question. So these galaxies that are being found by James Webb are very high redshift, or big look-back times, good fractions of the time towards the Big Bang. And they do seem to be highly evolved. They have evolved stars. You can do spectroscopy to show that they contain heavy elements. In astrophysics, we don't know of any way to generate heavy elements outside of stars. In the Big Bang and in the entire universe, when it's early, hot, and dense, you can generate helium, deuterium, lithium, and that's it, pretty much, the light elements and their isotopes. Heavy elements need stellar fusion, basically. So At the moment, we know of no other way to get heavy elements. Now, you can get them quite quickly, however, because even in the very early universe, when it was 10 or 20 times hotter and denser than it is now, you can have a first generation of stars form, and they will tend to be massive. And even if they contain no heavy elements, they will create heavy elements, eject them out into space. And their lifetimes will be short, few million years. So it actually doesn't take very long to send a pulse of heavy elements to create them and then seed them out into the intergalactic medium. And this can happen in the first 100 million years, or maybe even 50 million years of the universe.
The next question is from David Gold. In manufacturing quality control, the gold standard is 6 sigma, so it's about 3 defects per million. Why is it that astronomy accepts only 5 sigma as its gold standard for discovery?
It's a good question. So industrial production is a different beast, basically. In industrial production, you have a very controlled situation, and you need incredible levels of purity. To make silicon wafers, you need to control for the impurity of atoms in the lattice at a very low level, at a few parts per billion. That's actually more than 6 sigma. So there are industrial production processes, especially in the semiconductor industry, where the gold standard is not just 6 sigma, but 7 sigma. In a science in general, and in physics and astronomy in particular, you don't have to have that incredible level of rigor in your consistency, because you're not making an industrial process where you have to keep the failure rate incredibly low. You're just looking for the claim of a detection as opposed to not a detection. It's a binary thing. 5 sigma is pretty safe. In physics world, that was the criteria used to declare the Higgs boson detected in 2013, 2014. And the physicists actually waited a whole year. They gathered a year of data and pretty much saw a signal that they expected and anticipated as the Higgs, but it was only about 3.5 sigma, so they waited a whole year more of gathering data to get to the 5 sigma that physicists do and still consider the gold standard. Astronomers tend to be slightly sloppier. They publish results that are not always 5 sigma. Again, it's not a controlled experiment, and you can't pile up endless statistics and endless data because you're limited by photons in the universe. In astronomy, 5 sigma is definitely a solid detection. 4 sigma is marginal, and 3 sigma you wouldn't take to the bank. I don't think people would make a major discovery at all based on a 3 sigma detection.
Thank you very much. The next question is from Faisal, who would like to know, is it true that all or most of the stars visible to our eyes are binary stars or multiple star systems?
Yes, most stars in the universe, in our galaxy as we've inspected them and by extension elsewhere, are in binary or multiple systems. Single stars are in a minority, perhaps 20-25% single stars. Now, when we look at the bright stars of the night sky, we don't see them as binaries, because if they had a companion, it would be so close that it would be unresolvable by our eye. And the other thing, of course, that can happen is that the magnitude, the mass difference, and therefore the brightness difference between stars in a binary pair can be quite large. So if you had a star in the visible sky that was 5th magnitude, which is about a factor of 2 above the detection limit with the naked eye, then if its companion was more than 2 times fainter than it, you wouldn't see it. And so that's another reason why we don't see the night sky as full of binaries. They'd either have to be very wide, or the companion would have to be almost equally bright for us to see both of them.
The next question is from Arif Roni, who asks, which current research topic in astrobiology do you think is most likely to lead to a Nobel Prize in the future, and why?
Well, I think the first discovery of life beyond Earth will be Nobel Prize worthy. The discovery of the first exoplanet was the award of a Nobel Prize to Michel Mayor and Didier Queloz. So that's our precedent. And discovery of life in the universe is perhaps even more profound than the first exoplanet. What approach will lead to that detection first? That's really hard to tell. But the best guess is it's going to be by the inspection of the atmospheres of Earth-like planets for biomarkers or biosignatures. Some gases, not just one like oxygen, but a combination of gases, a whole suite of atmospheric chemistry that you can model and say definitively that that atmospheric composition could not be produced by geology or abiotically. That's a Nobel Prize worthy discovery. Who's going to do it? Where will it be done? What telescope will it be done with? Very hard to tell. It's a very competitive field. It could be from the James Webb, although the James Webb Space Telescope was not optimally designed for this experiment. It has limited spectral range in the infrared and can't combine that with optical data. Probably it's going to come from one of the 3 huge ground-based telescopes currently under construction.
The next question comes from Ravi Narasimhan, who asks, I understand that astronomers nowadays upload their observational requirements to facilities, and these instruments are largely designed, built, and operated by others. Do you think that there is something that's lost when scientists are decoupled from the tools they use? For example, not just ground-based telescopes that you just send requests for, but also space-based telescopes.
Yeah, it's a good point. And my colleagues, senior colleagues, we talk about this because in our professional careers, we've witnessed the transition from a situation for optical astronomy where you learned on small telescopes, you knew how the instruments worked, you took your own data, to a world where the telescopes are large, and for very understandable reasons, astronomers don't drive the telescope. The telescopes are very expensive, the instruments are very expensive, very delicate, and so you can't have all the visiting astronomers messing with the instrument. And it does create the separation that you're talking about. And I don't think that's a good thing, because being in touch with your data is actually a fundamental part of being a scientist. So it has become hands-off. Now for space observatories, it has to be hands-off because you can't control a space telescope. I've been at the Space Telescope Science Institute and been in the control room when the Hubble was unusually doing real-time observations, real-time ops as they call it. Most Hubble observations are made because you get your time awarded, you put your observations in the hopper, and an AI scheduler schedules them. The telescope takes the data and delivers it and uploads it onto the cloud. And then you download it and reduce it. So it was very hands-off. Occasionally, Hubble is doing a real-time observation, say of a supernova or a transient event, and then the astronomers actually do get to be in the control room, but they're not touching the telescope or running the telescope. The professional operators and NASA engineers are doing that. So it is generally true that astronomers are not in close contact with their data anymore. But that's the way it's been in physics for decades, so it's not that unusual in science.
Next question is from Georgia Paget, who's on with us live. This is a very recent discovery, so I don't know if you have seen the news or are able to comment on it, but there was recently, announced in the last 24 hours or so, a very large exoplanet that was orbiting around a relatively small star, and it's highly unusual. And she would just like it if you could explain this discovery and maybe talk about how something like that could happen where you get.
So I can't talk about that particular discovery. I haven't seen it, but I can talk about the general issue raised by large planets around small stars. So we've seen this before, and this is probably just an extreme example, because astronomers have been looking quite extensively for exoplanets around red dwarf stars, because most stars, of course, are much smaller and less massive and fainter than the sun, red dwarfs. And they have habitable zones, so it's not an unreasonable place to look for planets that might host life. And they are going to have large planets. Now, when we talk about a large planet and a small star, we should still remember that it's a much larger star, more massive star than the planet. So even a low-mass red dwarf with a Jupiter mass or few times Jupiter mass planet, that planet is still a few percent and no more of the star's mass. So it's all relative. So these are not enormous planets compared to their stars. They're just large compared to their stars in the solar system context.
Excellent. Thank you very much. The next question is from Dawn of the Force, who asks, has a question regarding how instruments and devices like JWST, how are they able to detect and use signatures to trace an exoplanet in another system?
So the exoplanets are not discovered by the James Webb Space Telescope. It's being used to follow up observations that were previously obtained with other telescopes. So the exoplanets James Webb studies were typically discovered by Kepler, or perhaps by ground-based observatories, or perhaps by the subsequent NASA satellite tests. And then the James Webb targets those exoplanets and brings to bear much larger light gathering power. Remember, James Webb is 6.5 meter aperture. Kepler was about 1 meter telescope. So you've got a lot more light gathering power, and you can do spectroscopy and you can work in the infrared. And so these are powerful capabilities that you bring to bear when you follow up an exoplanet that was detected by another instrument in another telescope.
Excellent, thank you. The next question is from Mr. P. Can you talk about if there's any new news, or what is the latest news from Enceladus? Do any researchers think that there may be geothermal vents under the ocean of that moon?
So Enceladus is a fascinating object, of course, and we learned pretty much all we know about Enceladus from the Cassini mission to Saturn. The Cassini mission had almost a 20-year run in the Saturn system from the mid-90s through the 2000s into the 2010s. And it observed it close, it did flybys, it observed the plumes. We've had subsequent imaging of Enceladus from the ground and from space telescopes, but we haven't added to the detailed information. So we would need another visit to progress on Enceladus, to ask the question of the nature of the vents or the nature of the outgassing material. Is it rich in organic materials and therefore could contain life? We will need a mission that goes to Enceladus. There's a NASA plan, a very early plan of NASA, and there's some private enterprise, some private philanthropy money that's interested in an Enceladus mission. But these are difficult missions. These are decade, 15-year projects, multi-billion dollars, and at the moment NASA's budget is so constrained that any Enceladus follow-up mission is really decades away, which is disappointing for many astrobiologists.
The next question is from Ben Swain, who asks, I've been reading about the black hole information paradox and the different ideas about whether information is lost or preserved. Do you have a view on which side you lean towards?
Well, it is a very active research question, and I would say there are dozens of research papers a year, and hundreds have been written on this whole issue. And it's, of course, unresolved, so people take different sides on it. My perspective is that information is essentially lost in the black hole. I do accept that the event horizon is an information membrane, a barrier, where things that go in can't come out, and therefore information in whatever form that goes in is lost forever. So I tend to view these are information sinks. People who want to escape that conclusion have to have some way of coding the information on the event horizon. That's like the holographic principle, which is an interesting idea, but it's unproven. And then there are various other ideas out there. So I guess I'm leaning to the point of view that the information is truly lost. It's not necessarily a paradox. It's a paradox because in quantum theory, the interaction of particles preserves information, whether the interaction goes forward or backward. And so when particles interact and then move in and out of or into a black hole, then you're losing information that in the normal world would be preserved. But it's not clear, given our theoretical understanding, that it's fair to call this a paradox.
The next question is from Jennifer, who asks, can you talk about the likelihood and or significance of discovering new elements?
We pretty much know the periodic table. So the periodic table ends with uranium and atomic number of 92, and that's the classic periodic table. There are the so-called transuranic elements, which the word tells you the answer, that these are elements with higher atomic numbers than uranium, and they now range up to, I forget, because there are new transuranics discovered every year or so. I think their numbers go up to 120, 121, 22 maybe. And these elements now have been named after not classical myths or given typical classical names, they were often named after famous physicists, including sometimes the people who discovered them. They're produced ephemerally in labs, mostly in the United States and in Russia and in Germany and Japan also. And by very challenging techniques of piling neutrons and particles into an already heavy atomic nucleus, you can very transiently create an even heavier nucleus, record its existence, and then it disappears or decays very quickly, sometimes in a tiny fraction of a second. So it's arguable what the use of the transuranic elements is, because they are all radioactive, they all decay very rapidly, and so you can't contain them or store them or do anything with them after they've been created.
The next question is from Hernan Reyes, who sent an email. NASA has issued a comprehensive astrobiology roadmap. The latest version was 2008. What are your thoughts on how this roadmap is being used or will be used? Are these, people sort of nations ignore other treaties that have been sort of established about research in space. So is this something that is still active and being, used as guidance, or are people going to basically ignore it?
The NASA astrobiology roadmaps, and there are plural because there have been a series of them and we're due for another one, are extremely useful in guiding the field. First of all, they result from the effort of usually over 100 scientists working in subgroups. So it's an enormous amount of expertise that goes into these roadmaps. And NASA has used them to guide and advise how it designs missions and prioritizes missions. So they have a very, very valuable role to play, these roadmaps. Now, these roadmaps don't talk about certain things except in passing, and one alluded to in the question is the nature of the sort of ethical concerns in astrobiology about contamination. When we go to another body in the solar system or beyond, might we contaminate it and therefore create a situation where if there's life on it, we don't know whether it came from contamination or was already there. And then the back contamination issue is probably more profound, because that's when we bring back material, say from Mars, and wonder if it might contaminate or become a pathogen on the Earth. So there are no UN treaties that deal with this kind of thing. There are working groups that could move towards a treaty on some of the ethical principles involved in space exploration and astrobiology. So at the moment it's a sort of self-policing thing. And most astrobiologists are trained and of the persuasion that conservation in general terms is a good thing. And so we do not want to despoil or sully or contaminate other worlds that we might travel to in the future.
The next question is from Justin Pro Gaming, who would like to know, is the white hole theory true? And if it is true, is there any connection between black holes and white holes?
We get this question quite often. White holes are hypothetical, purely theoretical. They're accommodated within general relativity, so they're not against physics as we understand it, but there's no evidence for a white hole. A white hole would be a rupture in space-time, possibly connecting to a quite disparate location in space-time. And space-time, as we measure it in the universe around us, is very smooth and featureless, and so there's no indication of complex topology or the kind of tessellations or perforations or complications that would lead to the presence of a white hole. Apart from that, the observational signature of a white hole is really hard to pin down, and in astronomy, any signature, any object that you might want to detect where there are a lot of false positives, that is, things that look like it or have the same signature but are not what you're looking for, those are difficult, and astronomers tend to avoid looking for such objects because you're just going to get fooled more of the time than you should.
The next question is from Saad, who's on with us live, who has this question. The singularity before the Big Bang, how would it appear to us, or can we think about something that existed without time and space? Did it possibly exist in a dimension other than the 4 dimensions that we know?
Well, the singularity is the origin, essentially, the inception of time and space. So it is true that at the point of the singularity, time and space have no meaning. They emerge as quantities we can measure and track after the Big Bang. Whether the singularity exists in a hyperdimensional space partly depends on whether string theory is correct, because string theory postulates that the three dimensions of space and one of time that are the basis of our current theories are parts of a larger landscape of multidimensional space-time going up typically to 11 dimensions. There's no evidence or experimental verification of that idea, but that would be the basis by which the Big Bang might be embedded in larger dimensionalities of space.
The next question is from Jidal, who asks, what are the leading theoretical models that attempt to explain the Hubble tension?
It's very hard to say because astronomers are pretty much waiting for this to be resolved. Theorists, of course, can always work on ideas and clever ideas. But it's also hard to put too much intellectual energy and theoretical work into something where you don't know what it is you're actually trying to explain. So at the moment, the best guess is there's some undetected or unrecognized systematic errors involved in one or other of the measurements that are discordant in the Hubble tension. And the Hubble tension is a disconnect at the level of less than 10% but highly significant between the expansion rate measured locally in the universe and the expansion rate measured in the distant universe through measurement of the background radiation. So I would say it's too soon to answer that question because there are no good theoretical ideas for something that we don't know whether it's a real effect yet.
The next question is from Arif Roni, who asks, what shift or change in theoretical understanding or scientific imagination created the urgency and conviction to pursue a massive project like LIGO to detect gravitational waves, which seems like it should be basically impossible?
Yes, it's a good question and a good point. LIGO is an extraordinarily ambitious project, and then kind of amazing that it was ever done and that it worked, because it's big science, it's very expensive, multi-billion-dollar mission experiment, two identical gravitational wave detectors on opposite sides of the United States, measuring its flexure in space-time caused by gravitational wave at the level of 1 part in 10 to the 18. That 1 part in a billion. That's extraordinary. That's by factors of thousands the most precise experiment of any kind in physics or any field in history. The impetus for LIGO and the fact that it happened at all comes from general relativity. It comes from the fact that one of the untested predictions of general relativity, a theory that passed all its other tests with flying colors, was the existence of gravitational waves, ripples in space-time. And so while this sat as an untested prediction, there was a lot of motivation to make that test, to do that detection. And I think it was the belief in general relativity as a foundational theory of gravity and this omission that we never looked for or detected gravitational waves that was the impetus behind the project. And the reason it got over the hump and got funded by a skeptical Congress was that the premier physicists, not just in the US but in the world, were involved in it. Kip Thorne, who's a preeminent gravitational theorist and professor at Caltech, and one of the Nobel Prize winning scientists behind the LIGO detections, he was often brought out to talk to Congress or legislators or to lobby for funding at a time when budgets were tight, because he was so eloquent about why this was an important experiment to do. And so his arguments and those of his colleagues really swayed some very skeptical legislators.
The next question is from Faisal, who asks, to what extent do meteorites, cosmic rocks, and Martian rocks retain their parts and molecules from their origins and protected from destructive solar and cosmic radiation?
So space rocks, because they're dense, and if they're of any significant size, their interior regions are sort of immune from solar radiation or cosmic rays or anything else happening out there. So as long as you're not talking about the surface regions or probably the initial few millimeters, perhaps up to a centimeter of a space rock, then you can be fairly confident, given the density of the rock and the limited ability of X-rays and cosmic rays and radiation to penetrate the rock, that that's pristine material. And since many of these rocks were formed at the beginning of the solar system, these are primordial rocks telling us about the solar system 4.5 billion years ago, and therefore they're very important in telling the story of how the solar system formed.
The next question is from Sharvan Kumar, who sent an email. My younger brother asked me a basic question. Why does the Earth rotate about its axis, and why is that axis tilted by 23.5 degrees? Is there any specific reason for the tilt?
So the reason for the rotation is because it reflects the angular momentum of the original cloud of gas and dust that formed the solar system. By far the majority of the mass of the solar system, over 99.9%, is the sun. And the sun is spinning about once a day, same as the Earth, and in the same sense, in the same orientation, so same angular momentum vector. And so the reason the Earth spins is because it formed from a disk of gas that had angular momentum, and so the Earth shares that angular momentum vector. The reason for the tilt is different. We don't entirely know the reason for the tilt. The Earth has a big moon, however, and the moon has influenced the Earth's tilt, and it was perhaps even the formation incident that led to the moon 50 million years or so after the Earth formed, caused by an impact, we think of a Mars-sized object with the infant Earth, that knocked the Earth off its axis, if you like, by some amount. But Mars has an axial tilt that's very similar to the Earth, so almost all the terrestrial planets have an axial tilt. The giant planets not so much. So it's not unusual to have an axial tilt for a planet.
The next question is from Zorn, who asks, what are your thoughts on the recently discovered dark galaxy candidates that seem to lack stars? Do they or could they challenge our current understanding of galaxy formation?
I think dark galaxies are not, they're interesting and they're enigmatic at some level, but they're not challenging our theory of galaxy formation. It is quite reasonable and plausible to have dark matter potential wells where the gas will concentrate and then stay cold, and so you don't have sufficient density of dark matter to induce collapse of the baryonic material to form stars. And so you can have essentially quiescent galaxies, galaxies that sit there with their sort of primordial gas composition, hydrogen and helium, where there hasn't been either an interaction to trigger star formation or sufficient central density to trigger star formation. So it's not implausible to have dark galaxies. I think it's very premature to say that it causes problems for galaxy formation. They are, however, very interesting because to astronomers, these galaxies are dark matter laboratories. They're probably the best places to measure the properties of dark matter.
The next question is from Gilmar Dematos, who asks, hello, Professor. Have any exoplanets been identified in the Magellanic Clouds?
Yes, there are some exoplanets that have now been found in external galaxies. There are exoplanets that have been found in Andromeda, M31, which is a lot further away than the Magellanic Clouds, and there are some found in the Magellanic Clouds. Now, these exoplanets are found in a sort of by statistical methods because we can't resolve enough angular detail in the Magellanic Clouds, even our nearest neighbors, or any other galaxies, to resolve stars in a cluster and pick out the exoplanets. So they have to be done either by statistical measure of transits or more often by a microlensing method. But yes, it is possible now to detect exoplanets beyond the Milky Way.
A kind of a follow-up question is, have black holes been found in any of our closest neighboring galaxies?
There are no black holes that we understand in the Magellanic Clouds, our nearest neighbor galaxies. They're very low mass and irregular. If they did have black holes, the black holes would maybe be 1,000 solar masses or a little more, and that's very hard to detect. So they actually could have black holes that are very low mass. We just haven't detected them so far. But our other neighboring galaxies in the local group, the two biggest ones are M31 and M33, do have black holes. And so we can indeed find black holes in among the nearest galaxies to the Milky Way, and we expect them to be in the center of every galaxy.
Excellent, thank you. The next question is from Sharvan Kumar, who asks, who would like to know about the latest discovery or claims about detecting the dimethyl sulfide. I can't read. It says DMS. Is it really possible to detect such compounds 124 light years away with our current observational instruments?
So, two parts to the answer. I mean, the first part is yes, it is possible to detect molecules like dimethyl sulfide in stars or in the atmospheres of planets that are 100 or more light years away, because James Webb is a large telescope, and when you observe transits, you have quite a lot of photons to work with, illuminated by the background star, of course. You're looking for absorption in the atmosphere of the exoplanet. So the experimental technique that leads to that observation is quite well understood and quite robust. The detection we're talking about, however, is not sturdy or robust because relative to the gold standard of 5 sigma, it's well under 5 sigma in either of the 2 years of observation. So the community as a whole has reacted to that claim, that detection of dimethyl sulfide, with a large degree of skepticism. It doesn't mean that it isn't there, that it's not possible, but that spectral region could have dozens of other molecules that could put a signature, that could give a signal at that same wavelength. And so you have to rule out other possible identifications of that signal, assuming the signal is right, and then more people will question the strength of the signal and just say that it's essentially noise, or that it's a way you fit the background, the baseline of your spectrum that led you to infer that there was a signal when there wasn't one.
The next question is from an email. Anjana asks, have people been able to detect antimatter in space?
Very briefly and very occasionally. So antimatter exists in the universe. We can create it on Earth, of course, with particle collisions. But in the universe, it's very rare. So antimatter is created in a situation of high energy collisions. If you have sufficient energy, you can generate electron-positron pairs, or if you have even more energy, you can generate protons and antiprotons. And we know that these antiparticles do exist. Cosmic rays, for example, have very high energy particles. And so very sparingly antimatter has been detected in space, single particles essentially. But there are no anti-objects, if you like. We have never detected an anti-planet or an anti-star or an anti-galaxy, and we essentially think they don't exist.
The next question, also an email, is dark matter also pulled in by black holes?
Yes, black holes pull in all matter, and they trap matter and radiation. And since dark matter has mass, then dark matter particles, whatever they are, whatever the dark matter is, will indeed be pulled into black hole. And so logically, the interior of a black hole, which we can't inspect because the event horizon is an information barrier, that interior contains normal matter, the kind we're made of, and dark matter as well. It's not clear in what relative proportions it does, because again, we can't inspect the black holes to find that out. But yes, dark matter is pulled into black holes just the way normal matter is.
The next question from Random Dude asks, why does it seem like we don't have scientists or discoveries today on the level of Einstein or Newton? Is there something going on, or what's your view on this?
It's an interesting question. It's a matter of debate among scientists and philosophers of science, of course. And I don't know what the answer to it is. I mean, it is a true statement that there are more scientists working today than have ever worked in the history of civilization. So you would think if brilliant discoveries and foundational science happens according to the population of people doing it, there should be more than ever. The countervailing trend, of course, is that we've made a lot of progress in science. So many things have been figured out and solved, and we have theories that are successful that don't need to be messed with, like the electromagnetic theory, for example, or the theory of the sort of weak and strong interactions in the atomic nucleus. We think those are pretty good. So that would imply that we're running out of major discoveries, and it's not that the scientists aren't smart enough, it's just that the low-hanging fruit, if you like, has already been plucked. And so the questions that we're trying to solve are now harder questions, like is string theory correct, like where's life in the universe, that will just be much more challenging to figure out. I think the truth is a little bit of both, actually.
Excellent. The next question is also going to be the last question for today because it is 11 o'clock, so we will be wrapping up here. Ernest Stelder would like to know if you can explain, he's heard of something called quantum loop gravity. Can you talk a little bit about what quantum loop gravity is and how it would work?
So quantum loop gravity, we keep this at a non-technical level, is an alternative theory of gravity that tries to go beyond general relativity and tries to do some manner of reconciling general relativity and quantum theory. And so there is significant theoretical work on new theories of gravity that incorporate quantum mechanics, and quantum loop gravity is one way of doing this. It's very dense mathematical theory. At the moment, it's not clear it makes unique predictions that would allow us to test it and distinguish it from general relativity itself. But it's a fairly active, if a modest, niche of theoretical work. There's probably a few dozen people working on it, and I see a few dozen papers a year coming out on that subject. Thanks again for your questions, covering a lot of ground as usual, and we have Matthew can say when the next sessions are, but we've arranged a couple. The spacing will be a little larger in the summer because of my travel, and it's just the summer, so things quieten down. But we do have a few sessions upcoming.
Yes, absolutely. Before you leave, make sure you hit the like button, that thumbs up button. That helps our videos get out to more people, and we get more views from those. So we would really appreciate it helping us with our reach. Yes, our next live session will be June 20th. And if you are getting the emails about those, fantastic, through our courses. If you subscribe to our channel and click the bell icon, you always hear about new events. You'll get a notification about our next live sessions. And if not, then scroll up to the top of the chat and join our Google email list. And I always send out reminders about the live sessions the day before, and then, the day of the live sessions. And that's how you can find out about more of those. So thank you so much for joining us today. We really appreciate it. Thanks for all of your questions. We will see you again on June 20th, and have a good rest of your week and weekend, everyone. Take care.